Hi y'all, welcome to section 4.9. Today we're going to be looking at related rates. And the first thing we need to do is just practice knowing how to write a rate of change. Okay, so this will be our first time where we're actually applying our derivative knowledge with real life problems. Okay, so let's jump in. So the first example, we're just going to be practice translating English sentences into calculus notation using differential notation. Okay, you always need to identify the variables, what's changing, and what their units are, and then we can make a statement about how fast that thing is changing. Okay, so here, for example, letter A, we're looking at a boy is growing 3 inches every year. Okay, so growing at the rate of 3 inches per year. So if we think about what is changing, that would be the height of the boy. So if we let h be the height, and maybe in parentheses we could put the units here. These are inches. Okay. The other thing that's varying for all of these problems will be time, because it's real life stuff. Okay, so we're talking about how fast something's changing over time. So t will be time for every single problem. And I'll be honest, I rarely write the time out because pretty much if you see a t, you know it's going to stand for time. Okay, but it is interesting because the units will vary for time, right? In this case, he was growing 3 inches per year, so our time is in terms of years. In other problems, it's going to be in terms of days or seconds, so our time obviously varies as well. So if John is growing, so obviously increasing over time, and that's a key word compared to like other problems, will be shrinking or decreasing. That will obviously indicate the sign of the rate of change. So if John is growing at the rate, we're going to talk about the rate of change of his height, so dh dt. The rate of change of his height with respect to time will equal, and it was 3, and it was positive 3 because growing. And then units are really important, so we're going to say dh dt will equal 3, and we'd say inches per year. Okay, so that would be like your answer for this problem. We're translating that sentence into a differential, really a differential equation, but dh dt is talking about the rate of change of the height with respect to time. And this is what we're going to be doing for every problem. We're going to have probably 2 or 3 of these that we'll have to translate. We're going to be making statements and then plugging them into equations. Okay. All right, letter B. My mutual fund is shrinking by $4 a day. Okay, so my mutual fund is shrinking by $4 a day. We want to write this as a rate of change. So obviously it's the amount of money in this mutual fund is what's changing. So maybe we could let A be the amount of money. So the amount in mutual fund, and that was in terms of dollars. Okay. T, time, in this case is in terms of days. Okay. So if we looked at my mutual fund is shrinking, so obviously that's a decreasing amount, so we would say that dA dt would equal -4. And dollars per day. You can go ahead and use the dollar symbol. So we just wrote a rate of change. Notice that you have it's called a differential equation. You have d of something over dt equals, and then the value that was provided for you, and your units. Okay. You guys ready to try one on your own? If you're ready to try, go ahead and try C. If not, go ahead and just follow along. So the radius of a circle is increasing by 4 feet per hour. So we have this circle that's magically increasing. So the thing that is varying is the radius. So let r equal the radius. And it looks like it was in terms of feet. Okay. Our time is in terms of hours. Okay. So if the radius of the circle is increasing, that indicates a positive derivative. So dr dt will equal +4. And it will be feet per hour. Okay. Hope this is making sense. Jot down any questions that you have as we go. If you guys want to pause and try the rest of these on your own and then come back and watch and see if you're right, that would sound great. So letter D, the volume of a cone is decreasing, keyword, by 2 cubic inches per second. Okay, so obviously here what's varying is the volume. Pretty popular to have a volume problem, and that was in terms of cubic inches. So inches cubed. And our t is in terms of seconds this time. So if the volume of the cone is decreasing, we know the rate of change needs to be negative. So our derivative, dv dt, will equal negative, and it was 2 inches cubed per second. All right. Now the last few I tried to write not as clearly in terms of like what's varying, so you do have to think maybe a little bit. These problems do require heavy thinking, so you need to make sure that you're really paying attention to the problems as you're trying to solve them. All right, the bathtub is filling up at a rate of 2 gallons per minute. So bathtub, we're talking about really the volume of the bathtub, right? So if we let V be the volume of the bathtub, or you could talk about the amount of water in the bathtub, that's totally fine. In this case, it's in gallons. Okay. Time is in terms of minutes. And it's filling up, right? So the amount is growing, so we know that the derivative, dv dt, should equal a positive value. And in this case, it was 2 gallons per minute. So increasing positive derivative, decreasing negative derivative. All right, letter F here. The balloon is deflating at a rate of 3 cubic centimeters per second. Okay, so the balloon, again, a balloon, we're not going to actually say let B equal the balloon. We're talking about the volume of the balloon, or the amount of air in the balloon. So let's stick with a nice mathematical term, volume. And it looks like we were looking at cubic centimeters, so centimeters cubed. And our time in this case was in terms of seconds. So if we look at the rate of change of the volume, if it was deflating, remember deflating indicates that our rate of change will be negative. So we would state that dv dt will equal a negative 3, and that would be centimeters cubed per second. Okay, so that is a skill that you'll have to do within problems. There'll rarely be a problem just like this where you're just translating that part. But those types of problems will be weaved into these free response problems, or perhaps just a multiple choice problem. Okay. Along with those skills, just writing how something is changing, a rate of change, we'll also have to practice implicit differentiation with respect to time of some pretty well-known formulas. Okay. These are not the only formulas that you'll have to implicitly differentiate with respect to time, but these are some of the more popular ones. Okay, so A equals pi r squared. Hopefully we recognize that as the area of a circle. If we are going to be talking about, like on that one of the last examples, we talked about this magic circle that the radius was increasing at some rate. Okay, we're going to be talking about real life problems of like an oil slick that is growing in a circular fashion, or bacteria that's growing in a circular petri dish and it's growing in a circular fashion. We talk about how fast that colony or that oil slick is growing, okay, then we'll have to implicitly differentiate the area formula of the circle. So area equals pi r squared, okay. Hopefully we're clear that if the radius was changing and getting bigger or smaller, that would affect the area of that circle. So both the r and the a would be changing, okay. This is where we get into related rates, and why this is called related rates is that we're going to be looking at how fast the area is changing, dA dt, and compare that to how fast the radius is changing, dr dt. Okay? So you should always find yourself with at least 2 rates within each formula. If you only find 1 rate, realize that it's not a related rates problem because you don't have 2 rates that are related. At least 2 rates, 2 or more. Okay? So chain rule will show up in every single problem, and so you have to really be careful and watch out for chain rule. Okay? So I'm going to take the derivative of both sides of this equation with respect to time. So any variable, I'll need to say times d that variable over dt. Okay. So I have the derivative of area with respect to time is truly just dA dt, okay, equals pi r squared. Now pi is not a variable. Pi is a number, right? Approximately 3.14159. But just think of it as 2 or 3 or 4. It's just a number out in front. If you're taking the derivative of a number times something squared, you're just going to use power rule. So you're going to pop that 2 out in front, keep that number there, which happens to be pi. R will decrease now to the first power. Okay? But now this whole implicit differentiation, we're taking the derivative of r with respect to time. So we have to say times dr dt. Okay. So this again is just one little part of the related rates problems. We'll be doing this and then we'll do more things from there, okay? But it's important at this step that you realize that here's the rate of change of the radius and here's the rate of change of the area, and we're relating them in this equation. Okay, that's why these are called related rates. Okay, if you don't know why you get this, this is like off to the side. If r equals something, and we don't know what r equals, but we know that there's a t in there. And so if I'm talking about taking the derivative of this function and I know it has a t in it, all I could call the derivative of that thing would be dr dt. I could call it r prime. It's just not as informational in terms of what we're taking the derivative with respect to. Okay? And so that's why it's, especially now that we've hit related rates, it's always more useful to use the d blank over d blank notation than the prime notation. It's just more informational. It'll tell you what variable you're taking the derivative with respect to. I don't know if we're ready to try letter B on your own. If you are, go ahead and give it a shot. C equals 2 pi r. So there's only two things varying here, the c and the r. And hopefully you recognize this as the circumference of the circle. Okay, the circumference will always equal twice pi times the radius. So if we want to implicitly differentiate with respect to time, the derivative of c with respect to time would be dc dt. Okay. And over here the derivative of 2 pi r. 2 and pi are just numbers, so those are going to stay. R is being raised to the first, so you're just popping a 1 out in front. So 1 times 2 pi. So 1 times 2 pi is just 2 pi. And then the r would essentially disappear if you were taking the derivative just with respect to r. But we're taking the derivative with respect to time. So the r is gone, it's just the coefficient, but times the derivative of r with respect to t. There's that chain rule piece again. Okay. So every time you're taking the derivative of a letter, a variable, you'll have to multiply that by the derivative of that letter with respect to time. Every time. Okay? It's just like what we did with the in section 4.8 with implicit differentiation. Every time we took the derivative in that section, we were taking it with respect to x. So anytime there was a y, we had to say times dy dx. Okay? Hopefully we recognize this guy, a squared plus b squared equals c squared, Pythagorean theorem for right triangles. This will actually probably be the most used. We have some great baseball problems, and baseballs are squares that have nice right triangles. So those will be nice right triangle problems. Also, if we have cars or things that are traveling in horizontal and vertical directions, they create nice right triangles, and we'll use Pythagorean theorem. So we'll actually use this guy a lot. Okay, so a squared plus b squared equals c squared. We're taking the derivative of each term with respect to time, t. So you first have to see what it truly is sitting here is a squared. So something squared, the derivative will still be 2 times something to the first, times the derivative of that something. So times dA dt. Okay, it's really not that different than what we've been doing. You just want to see this as something squared, and then inside happened to be something else. There was another function. We just don't see it right now. So we just hold its place with dA dt. Plus b squared, take the derivative of that, we'll pop the 2 out in front, 2b times dB dt equals c squared, pop the 2 out in front, 2 times c times dc dt. Every time you take the derivative of the Pythagorean theorem, this is what you should get. Okay. Now, we want to talk about how we could simplify this. Obviously, we could divide every single term by 2, and if we divide every single term by 2, it'll reduce down. So we'll get a times the rate of change of a plus b times the rate of change of b will equal c times the rate of change of c. Okay, and so really, so there's going to be kind of like 6 parts. You'll have your a value, you'll have your rate of change of a, your b, your rate of change of b, and your c, your rate of change of c. So out of those 6 pieces, pretty much you'll be given, or you'll be able to find out 5 of them, and the other one is what you'll be solving for. Okay, so this will never be like the final answer to a problem, but you'll be plugging in and then simplifying for one of those unknowns. Hope this is making sense, y'all. Letter D. I'd say try this on your own, but be careful. If you try it on your own, make sure you recognize that it's a product of 2 functions. Hopefully we recognize this. Area equals base times height, nice area of a rectangle. So the rate of change of the area will be dA dt with respect to time. And then base times height, we'll have to use product rule. So the derivative of the first, the derivative of the base, would be dB dt times the second, h. product rules plus the first, b, times the derivative of the second. So the derivative of h, dh dt. Again, here in this formula, there'd be 5 pieces: dA dt, dB dt, h, b, and dH dt. Out of those 5, you would need to know 4 of them to solve for the 5th one. All right, letter E, hopefully we recognize that as the perimeter of a rectangle. Perimeter equals 2w plus 2l. So why don't you go and try this one on your own. So we're going to take the derivative with respect to time. So the derivative of p with respect to time would be dp dt. The derivative of 2 times something will just be 2 times the derivative of that something. So dw dt. And then same thing over here, the derivative of 2 times something would just be 2 times the derivative of that something. So times dl dt. And letter F, volume equals 4/3 pi r cubed. Hopefully you recognize that as the volume of a sphere. I actually have seen that on the AP test, and they will provide it for you. Note, the volume of the sphere is, and they'll give it to you, but you may want to memorize that along with your other basic formulas. Okay, so dV dt, the rate of change of the volume with respect to time, 4/3 pi, just numbers, right? So those are coefficients, you're just going to bring those down. R is the only thing that's varying, the radius. Okay, so if we pop that 3 out in front, 3 times 4/3 pi, r needs to be decreased by 1, so r squared. And remember, if you thought this was the answer, you just have a dV dt. This is one rate. Where's your other rate? Okay, remember, this is called related rates. There has to be another rate, at least one more, that you're relating it to. Okay, you had this variable r, you need to say, oh, times dr dt. Okay, so now you have the rate of change of the volume, and you're relating it to the rate of change of the radius. Okay, so you can see that relationship here. Here, the 3's would cancel, and that's fine. Oftentimes from here, you're going to be solving for one of the unknowns. So actually, let's go ahead and solve this guy for dr dt. If I wanted to get this guy all by itself, dr dt, I would solve him by dividing through by 4 pi r squared on both sides. So I could state that the rate of change of the radius, dr dt, would always equal dV dt, the rate of change of the volume, divided by 4 pi r squared. Okay. The good thing is here, y'all, I know we've been discussing the algebra in terms of taking a fraction, dividing it by another fraction. Most of the time, you'll be given, or you'll be able to figure out this value, and you'll actually be plugging in a number right there. So you won't have to worry about, if that dt should go downstairs. You actually want to treat this all as one piece, for now. Okay, we will learn that we can separate those, but for now we're pretty much looking at the rate of change of the volume with respect to time, and we'll be plugging in points or values for that. Okay, so I think this is long enough for the first part of section 4.9. We'll pick up from here tomorrow. Okay, good luck, y'all.